Okay. Hi everyone. First, I'd like to give a higher level overview of the talk today. I want to briefly introduce higher order abstract syntax and also first order abstract syntax. And then I want to talk about the type checking of dependency type programming languages using higher order abstract syntax and the problems. And I'll give a demo of my proposed solution in a implementation of a programming language. And I'll talk about some related work and explain what's the point of doing all of this. So I'll start with syntax with binding. So uh, when we represent the syntax of a type series, we usually have to deal with binders. So for instance, let me write a definition of a syntax tree. So it will be, so we'll define a type of term, which represents the terms, and it will have the following constructors. Um, it will have um, applications, which takes two terms, and lambda, which has a lambda body. Um, so this is a naive way of writing that. And uh, and also we have something to deal with variables. And we want this term to have the following properties. We want to be able to check alpha equivalence and beta equivalence. So when we think about this term abstractly, we use the lambda calculus notations. We write like lambda x, lambda y dot xy for this expression. And this corresponds to a lamb where the body of the lamb is also a lamb. And then the body is an application of two variables. And we want to be able to test the equality of them such that we can equate things up to renaming of these variables. So one way of doing so is to use cleverly track the variables, which is not nice, and there are lots of well-established techniques to deal with this. So does anyone know what is the Brown index? Okay, let me assume familiarity with the Brown indices. So it basically represents, instead of using the variable names, we use a number between the occurrence of the variable and the occurrence of the binder. How many we count the number of bindings between them as a number to represent these references. So so these terms will be instead represented as lambda 1 by 0, and this lambda term will also be represented using the same term, and we no longer have to keep track of the name bind, which is nice. So this representation, written as the syntax tree definition, will involving two more, actually one more constructor called bound. So that for bound variables, that takes a natural number to return. And we also need to deal with free variables. So when we do this equality checking, it's usually under a context. So we can have like variable A of type big A. In the context, I have lambda x of x applied by A. And x is bound, so it can be replaced with a Brown index. But A here is it's not really clear how do we do this in the Brown indices. And I think the best way to do it is to still represent these three variables from the context using some names or unique IDs. So in the same context, I can have a different term. And I can test their equality easily. And I can also apply weakening. for free. So I can insert variables to the context, and that does not affect the AST. So so we'll have one more constructor called free, which takes a string, let's say, and returns a term. So that's the syntax definition. This method is called locally nameless. And it's called locally nameless, I think it's because the local variables, the bound variables are nameless, and the other ones are not nameless. They have a variable name.
In terms of the bottom, do you need to apply y?
Yes. That's what I meant to write. So this is one way to represent the syntax. The other way is called higher order abstract syntax. So instead of using the numbers, we say data term, and we copy the application because that's just the same. And for lambdas, we'll store a function in my meta language. So I'm writing this AST in the language. I call that the meta language. And the language I'm using, the language whose AST is being represented by this data structure is called the object language. So I represent the lambda of the object language using the lambdas in the meta language. And I also need to deal with free variables. So the intended way of using this term is, say, I want to write the lambda expression x, y, and I apply x with y and with a free variable from the context. And that all corresponds to a lamb with a lambda from a meta language, and I'll bind x. And then I return another lambda because the lambda constructor wants me to return a lambda. And I bind y, and I return the application of x and y, which are both variables from the context of the meta language. Then applied by the free variable a. By doing that, we can implement alpha conversion, like the equality test, even more easily, because actually not so much more easily, but equivalently convenient, because we also don't keep track of the variables. When we need to compare two lambdas, we just make the same free variable and apply that to both lambdas. Sorry?
So here, you're assuming you don't have a possibility checker?
Yeah.
That is okay.
You don't have to, suppose this is a practical programming language. So you start with unsound type system, and then non-normalization is not too much of a problem. Any other questions? Okay, does things make sense so far? I think people are high order abstract syntax. The idea originates from the church's simple theory of types, where you represent the statement of a proposition using the binder structure in the logic, and also Martin-Log type theory. Then it's adopted in logical framework, which encourage the use of this style to represent syntax in the object, which works very nicely. And then it's incorporated into logical programming by Brent Fanning. But I'll explain these related things in a bit. So we have two different representations of syntax, and when do we use one compared to the others? And we need to think about what can we do with them. And what kind of operations do we need when we implement a type checker or an interpreter? So in practical implementation of type checkers, we'll need to have something called meta variables, where it does not mean meta variables in the literal sense, but it means like holes or omitted subprograms that can be inferred during type checking. And we also need to deal with general recursion, which is usually a syntax for like less general recursion, but on the surface syntax, we'll have it is generally it is a good practice to write well like the general recursive syntax. So for instance, when we write the addition of natural numbers, and in the second case of addition, we kind of match on the parameters, and we'll recursively call addition in the return in the function body. And when we type check this definition, we'll first have to add the add function into the context and check the function body with add in the context. And after type checking, we'll replace add with the actual definition of add. And when it goes into mutual recursions, this is more complicated. And a convenient way to implement this is to make the reference to add a mutable AST node. So after type checking, you assign the function body to add, and then add will get the desired operational state. It will reduce the function body. But while checking add itself, it does not reduce because it doesn't have a body yet. So this is one way to implement recursive functions. And when you have type inference in these languages, so for instance, when you have the identity function, the type is for all A, and it takes an A and returns an A. But you want to omit the type, because whenever you apply ID with some like a natural number, it is clear that what the type is. So usually omit it and let the type checker insert the value of A here. So the type checker will translate this term into ID applied by an unknown type A, and then applied by 1. And then in the type checking of Y, it will see if this value is equal to the type of 1. And then it will solve the value of A. And this thing in the AST is a mutable node. And there are other use cases of mutable ASTs which are even more exotic, but these are the two I think they are most common in type checkers. And also we need to be able to evaluate code in type checking. So there are two needs. We want mutations and we want evaluation. Well, mutation also includes traversal of the term, and like you can mutate the term by like traversing the term and replacing one subnode with another. That's another way to do it. But, yeah, so I need to do these two things. And how are these two representations of AST good at these two things? So let's take this locally named expression. It is easy to do a mutation on this AST because the entire AST is basically a tree, and we can just replace the nodes of a tree by like using any methods like pattern matching and stuff. And evaluation in this language is a bit uh, complicated because when you evaluation usually means you have to beta reduce the lambda expressions applied by. So when you see an app of a lamb with a body, where body is the name of a term applied by something, you want to step it to something which is body but like substitute a. So it will replace the occurrence of the lambda binder inside body. So this is usually implemented using by traversing the AST of body and keep track of the index you are working on and selectively replace some bound variables with A. And so this requires traverse. So let me make a table of these methods. Where is a good place for me? Can I erase this? Yes.
So you said mutation is very easy.
Yeah.
Do you also need to care about variable structures? Or do you
Both of these languages avoid the name capturing issues
because of the
because this is nameless, so there's no bound names.
okay.
And this is in the meta language. So when you compile, they turn into some. When you compile this AST, this function becomes some assembly code, and the variables you can say they are represented using some.
That's the LCs, which are just around in this.
Yeah, the stacking this is really just yeah. So you make a table for mutation. Here's locally nameless and higher order accessing. For mutation, it's easy, and for evaluation, it requires traversal. And for what about higher order syntax? When we want to mutate a term, like I want to say I have a lambda term. I want to have like this unknown term inside of it, and I want to replace it with the solution of it. Say I have like an assignment today to do some other term. Say I want to instantiate this assignment into the function body. Then when we traverse the term, we'll see, well, we see a lambda expression. And then we're kind of in trouble here because the code of this lambda expression is written in the meta language. And when you run the interpreter or the compiler, the function body is represented usually in an inaccessible way. Like for instance, if this is written in C, then the function body of this will be a piece of machine code. And the substitution here means replacing a piece of machine code that returns this thing with a piece of machine code that returns this thing. And that will be extremely complicated. And in like safer languages, where you cannot access the code you're running, then you cannot even do this. And there, you can argue that you can, one way of doing this is when we do the traversal, we write a new lambda. Say I want to write a function that replaces this A with F. So when it sees a lambda expression where the body is a function, I can return a new function that introduces X, having a lambda. And then it applies X to F. And then you get the return value of it. And then you do the substitution. You replace this question mark A thing with them. And you implement a substitution that does not that ignores lambdas. But this is not nice because when we implement these programming languages, the meta language is usually a call by value language, which means it does not evaluate the body of a lambda expression. So when you do a replacement, every lambda will become lambdas, and the action of doing this replacement will be kept in the body of these lambdas. So later on in the code, when you do a bunch of replacements, the body of these lambdas will be a gigantic sequence of introducing a lambda, apply substitution, and then introduce a lambda, and apply that, and then apply a substitution. Like when you do this substitution once, and you call the lambda twice, the substitution will be executed twice, which is not nice. But if your meta language has the ability to reduce under binders, to simplify the code under binders, then this is as efficient as the nameless. But in fact, it's more efficient because it does not need to traverse the term. It returns the function body directly by applying function. And I think Frank's contribution is incorporating this in the context of logical programming. Is that right? Mm-hmm. Okay. But for our purpose, we're writing usually we write interpreter is in the call by value language. So this method has its problem. So for mutation in high order abstract syntax is extremely important. And evaluation is very easy because it just calls a meta level function. It does not need to traverse anything. So it's basically O1. So it looks like if we want efficient mutation, we should use 1. If we want efficient evaluation, we should use the other. So this seems not nice, right? But when you actually think about it, the mutation is only needed in the type checking. So the examples I presented, there are recursive calls, which only happens when before the function is finished type checking. And when you need evaluation, you need it everywhere. So here's the plan. Okay, so here's the plan. We can combine these two data structures. And when we do type checking, we use locally nameless. It's all locally nameless. But when we finish type checking, we know all terms are settled. All the function bodies will not be changed again. We can use some runtime code generation technique to generate the function body of these lambdas from these locally nameless functions. And we get efficient evaluation. So the combined AST will look like this. So instead of having, when we look at these two things, two ASTs, the lamb has two possible implementations. So just replace one of them. We call it like closure, and we define closure to be either a locally nameless closure, which is just a term, or it's a higher order abstract syntax closure, which takes a meta level function. And when type checking, we use this variant, and after type checking, we translate as much as possible this variant to the other. And then to implement reduction, we look at lambda, and we look at lambda in the application, and we case on the implementation of closures. For this, we apply the traditional substitution. For this, we just call the function here. And this is the syntax definition I'm proposing we used. And I want to demonstrate how, yes.
For the evaluation of higher order abstract syntax,
yes.
I mean, like the The time complexity will still like depend on the size of the term, like its values of the meta language.
Yes.
Yeah.
So you will like construct the AST
Yeah.
right away
Yeah.
instead of having to traverse.
Yeah.
So suppose you get memory allocation is O0, then it's O1.
Yeah.
It depends on how efficient your memory language. It also depends on how efficient your meta language is. If your meta language has poor optimization for closures, then you have poor performance for evaluating terms in higher order abstract syntax. But if your meta language is very good, like if your meta language has like JIT compiler, then you get JIT compilation for your language for free, which is nice. And you can also think of the process of compiling this locally nameless term into higher order abstract syntax as a form of JIT compilation. So you get like a two-layer JIT. You write one JIT and you use the meta language of the JIT of the meta language, which like gives you machine code targeting compiler for language. It's very nice. So I want to demo this thing now. I want to show a piece of code. It's a red-black tree implementation that sorts a list. So none of these matters. We only need to look at the last function. It takes a list of natural numbers and it returns a list of natural numbers. And the way of the function is defined by sorting the list. And the sorting is implemented by a red-black tree, because I found red-black tree is the best sorting algorithm in a dependency type language, because all of the other sorting algorithm requires the strong induction. Like merge sort, the recursive calls are strong induction, and quick sort also has the same property. But the tree sort is all structured without recursion, which is very nice. And let's see. And so this is the code, and here's the AST that resembles this thing. So I have a closure type, and it has two implementations. It actually has three, but one of them doesn't matter. So there's JIT and locally nameless. And locally nameless basically has a term in its body. And when you apply it, it will call the substitution function on it. And the other JIT variant, it takes the unary operator basically means a function from term to term. So this is a language that does not have first class function, so I have to use this. But you can see that in the application, it just calls the application on the lambda, which resembles that. And there's also the const function. So during type checking, we sometimes generate functions that are known to be constant. So I have a dedicated representation of that. And when we apply, we just ignore the parameter. So let's first look at the pure locally nameless interpreter. So it first type checks the tree sort code, and it will use the Java random number generator to generate 50 random numbers between 0 and 400. And then I translate that into object language term in this make list function. And then I apply the sorting algorithm on this list. So here's the code. I call the normalize function on the function call of tree sort net with the list. And note that the size of the list is 50. And how fast is it? So here's the result of sorting the array, in case we're not sure about if the result is correct or not. We can also print the original array, but I didn't write it. I can just do it right now. So the original array is a random array, and it's indeed sorted. And sorting length of 50 list takes 365 milliseconds, and running it more times, it becomes faster and faster because JVM, the Java virtual machine, has a JIT compiler that can optimize your code on the fly. So it becomes faster and faster. I have no idea why it's start to backtrack the performance later. But so this is basically it. And, yeah, it's tired. Now here's the translated implementation. So I'll use the default compiler of the language, so by default the language will do the translation into higher order abstract syntax. So this code you cannot see much translation because it's built in a compiler function. And in the other version, I have to do a lot of manual work to avoid the thing being compiled. So basically, I have to manually re-implement type checker again. But this code is you cannot see much, but you can see the class loader here, which is JVM's the mechanism for loading a class at runtime. It compiles the code, loads it, and do the same thing. I call the sorting function, but instead this time I sorted with a list of 500 elements. And so remember that this time, on average, it takes 169 milliseconds. And when I run the JITted version, so you can see that it calls invoke on the definition, and invoke is I'll show you later. So the list is very long, but it's taking orders of magnitude shorter amount of time compared to the other version, which is very nice. So this is the power, the performance power, and the practical power of higher order abstract syntax. It's really fast. And I wrote another test case which generates a different list every time I run it, and the performance is very similar. It's very similar. And it's even faster for something. Maybe it didn't print the list, so it's even faster. And let's look at how much time is actually taken in a traversal, because this is just a fair measure of the system time. I can also show the CPU time taken by the evaluation. So if we profile this varying input, well, actually, let me profile the same input function, because the other one also measures the time taken to generate the random numbers. If we look at the flame graph, and here is the invoke, this invoke call here. It corresponds to this node in the tree. So it's in the same input function, and it's the invoke. And profile many is the other function that calls it many times. We can just look at the invoke function, which calls it once. And you can see that the function is in a very cryptic class name, not invoke. And it cannot jump to source. Let me show you the source. So there's no source. There's only bytecode. It corresponds to this tree sort net function. And the invoke method returns tree sort dot invoke with something else. So we can look at it. But it also calls tree sort dot invoke. This corresponds to the implementation where tree sort net is basically calling another function, and tree sort is also calling the arbitrary to list. And we can look at some other interesting functions like balance right, the balancing function of the red black tree. And then it has a more interesting function body. So it has pattern matching in the function body. So it translates the patterns into a state machine where it traverses the term and tries to check, see if they are some kind of constructors, and they'll return These are all the pattern matching code for the translation, and it binds the terms in the input by assigning these local variables. And then I do a switch case on which clause am I matching. The default case is if I'm stuck, I return the call to myself. Otherwise, I return like a constructor call on something. So that's it. That's the pattern matching implementation. So usually, yes.
There's some clarification to make sure when you say what you're comparing here.
Yeah.
The type as file is everyone.
Yeah.
Are you running basically the same like RB?
It's the same file.
The same IDA program?
Yes.
But using the local mainwares.
Yes. Yeah.
Okay. And there you use it.
Yeah. So it uses a traversal based normalizer. And see the implementation is basically a big switch case, a big pattern matching on the code, and returns like, for instance, when it sees a function. So when it sees like a pattern matching expression, it will try to unfold it by traversing it. So this is basically a traversal function. And yeah, that's it. And in the JIT compiled version, when we sort a list, it takes 56 milliseconds. And we can run the other one with a profiler. Note that this is 10 times smaller the input size. And it takes it's this function. So in the profile function, it takes 408 milliseconds. So that's the comparison. So because running the JIT version on the same size input is not much faster than this. I want to fully show the potential of this mechanism. And what's even funnier is that because JVM does not have tail call optimization for security purposes, this thing runs extremely fast, but also stack overflows extremely fast. So if I increase the size even larger, it still runs, and it's not so much slower. But if I make it very, very large, like this, it will stack overflow in a very short amount of time, basically. And I'm looking to implement some tail call optimization at the bytecode level. Yeah, it prints the original list. It's very long, and then it stack overflows. Yeah. So that's all I want to share about this work. So HOAS impact I didn't invent it. This hybrid architecture, it's my thought, but it's also not my original idea. So let me give a brief literature review on this subject. Let me erase this. So there is a famous proof assistant called log, formerly known as CORE, and it has two tactics. Yes, two tactics. One called VM compute and one called native. VM compute and native compute. Both of them have a related paper. And so they have some similar ideas to this. VM compute translates your term into some abstract machine. And native compute translates your code into some OCaml. And they'll run the code and translate it back to the term. This architecture does not have the translate back process because we have these things in our core AST, but they implement that externally. So the translation back function is crucial, and it's not correctly implemented. Native compute is the source of soundless processing because their native code is untyped. So when you translate back, you have to somehow infer the types, and sometimes you got it wrong. And in our case, we operate on AST, so we have a larger, heavier AST. We have a simpler AST. And VM compute is very good because the abstract machine definition can be easily, relatively easier, easily, where native compute is usually impossible because then you have to formalize the entire OCaml operational semantics, which is not realistic. And also, when you add new language features, you get, you don't have to touch the binding structure. So when you add new language features, you have to extend the native compute, which is engineering, more engineering effort. And there's also a language called MLand, written by some person on the internet, which didn't publish it. They translate to higher order abstract syndrome. So they use a completely different AST. So we have a locally nameless AST, and then we translate the entire program into higher order abstract syntax, just for the sake of normalizing a single term. They don't incorporate that into type checking. So there's a difference. MLand is mentioned in John Sterling's talk in the first workshop in implementations of type systems. It's not mentioned anywhere else in the academia. So why is a sorting algorithm relevant? I want to give some remarks. So why is this matter? Because sorting algorithm is crucial for implementing a ring solver. So when we do the ring solver, does anyone know how to implement a ring solver? You usually normalize the ring expression into some kind of sorted form. And then you, while you normalize it, you generate the equality proof that the input is equal to the output. And you connect the normalization of two sides. If two expressions normalize to the same normal form, then they are, in the ring sense, according to the ring axioms, they are equal. So the sorting is essential in this ring solver. And in the Arran programming language, the ring solver is implemented using the same red-black tree. So actually, my red-black tree sort is a transliteration of their code. And so they have these functions that says like, I interpreted things into normal form. It's equivalent to interpreting them into the sorted version of the normal form. And this sort is the red-black tree sort. So you can see the function names are even the same. So this is efficient. And the Lin and Agda, unfortunately, they have bubble sort. And the bubble sort is not bubble sort. When they normalize, they do a comparison and they shift. So when you have like a plus a squared, it will normalize to a squared plus a. And there's a comparison happening during the normalization. And this, in the big scale, is a bubble sort. And it took me a while to figure out because I was trying to search for a sort function in this file. And the only occurrence is the comment saying sorting the subterms. Unfortunately, not helped by anything. And the other sort does not mean sorting. It means sorting in the sense of type theory. And Agda does the same thing. And without even mentioning sorting, there's a comparison function called here. It's the tactic.ringsolver.car. There's another deprecated ring solver, but I demo this one, which is the latest one. So if we want to make a practical proof assistant efficient and write tactics using your language, then having an efficient sorting is very important. And to have an efficient sorting, you might want the efficient evaluation of your program language. That's all I want to say. Thank you so much for your attention.
Yes, I have two questions. The first one is, have you tried this in the Milton compiler? Because they use defunctionalization, which is a very efficient representation of higher functions.
I haven't.
Because it might obviate the JIT compilation that we're doing here in some sense, because they have first order, they use Reynolds technique basically to translate the high order program to first order one. They apply that to C. So it would be interesting to see if you get similar result from that.
Yeah, of course. JVM does not have this optimization for high order function.
Yeah.
And that's interesting, but does ML have dynamic runtime code generation?
Well, I don't think the compiler does.
Okay.
But it does defunctionalization, so it does create a first order program out of a higher.
I see.
Yes. And the other, you may have mentioned this, I zoned out for a few minutes there, but what about normalization by evaluation?
I think what I implement is essentially normalization by evaluation, but without the dedicated type for values. It just pervasively apply the inclusion from values. So I think that's how I think about it.
Okay, but isn't that normalization by evaluation type directed?
Yes, my evaluation is also type driven.
Okay.
It has a similar data structure as value in the term. And when I do the normalize, well, actually my normalization is not type directed, but my conversion checking is type directed. So I can do some type directed reduction in the conversion checker. But the normalizer tries to resemble the operational semantics, which is untyped.
Yes. And just to make one more note about Milton, I think that compiler is the whole program compiler. I don't know how well it was
I see.
setting like this, but I haven't thought through that well.
When I first want to implement this, I try to look up the language that has dynamic runtime code generation. And what I found, the most reliable options I found are V8 and JVM and CLR. And by the time, I don't trust Microsoft that much, and I don't want to touch JavaScript. So I picked Java, which I think it's relatively better than JavaScript.